Hello, I'm Julian. This video will take you through my journey of learning procedural generation on my own using noise. Although the code includes Perlin noise, as you can see on the left, I do not actually explain it because it is not mine. I include it from a GitHub repository. I only use it to compare to my noise. Okay, with that out of the way, let me show you how it works. Okay, so we have basic noise, we have random noise, we have linear wave noise, and then finally we have jukebox noise, my own algorithm. Okay, I can also change the color, so I can turn this into this, and I can do so for all the others, but the results aren't as good as this. And if we compare it to Perlin noise, it will look something like this. Okay, as you can see, it's quite jagged, so to make it less so, we can increase its smoothness. Okay, as you can see, each time I regenerate it, it gets smoother and smoother. I can also increase the iterations, so this will be combined with another, how should I call it, noise map. But the results aren't great. I imagine they could be for other methods such as this or this random noise. You can see it's turning out a lot better than the initial version, like this. Okay, so now that we know how this works, let me explain to you how this is displayed. I'm displaying this using SDL2, and each pixel of the image is part of an array. So when we modify that array, each pixel of the image changes. Okay, now let's look at the code. Okay, this is the main method. Not the main method, never mind, this is the self-renderer. This is the main method. First, we start with including SDL2. This is horrible to implement. Then we have the screen size, X, Y, 1000 pixels by 1000 pixels. We have the window, we have the renderer. We initialize the renderer, or everything, window and renderer. Then we have our self-renderer, which is our own method, which handles the display of the array to the pixels of the screen. Then we have a bunch of values. While quit is false, you can see it right here. This handles you quitting the window. So when you press the red button, it quits. Then we have an event, so we can detect button presses. We have the smoothness, iterations, color, the current noise, and if we should regenerate or not. Okay, now here we have, if G is pressed, we make basic noise. If H, we make random noise. If J, linear noise, and K, jukebox noise. And with L, it's Perlin noise. It's called Berlin because for some reason CMake is very angry at me and will not let me name anything Perlin noise. Otherwise, it will not run. So we have to do with Berlin. Then we have the setting of the smoothness. And here we set regenerate to 1, meaning that if we change these values right here, smoothness, iterations, color, etc., we should regenerate the noise. Okay, these are the case for the regeneration. Okay, and here we destroy the renderer, destroy the window, and we quit. It's pretty much main method. Okay, now let's move on to the second most important method, the self-renderer. Okay, it takes in the X value of the screen, Y value, the size of it, X times Y, a vector of colors, which is also a thing that we create. A color has an RGB value and a transparency value and a location. So it's not only a color, it also contains its location on the screen. So each pixel is technically a color. We have getters and setters, pretty basics, and a constructor. Then we have our renderer, obviously, and constructor. Easy, we don't even, we initialize it right here. You can see it's pretty basic. We just set every color to white and set the private values. Then we have the display, which takes every color in the colors array and draws it to the window. Now, set pixel is actually never used because set pixel works for one individual pixel, and it would be less efficient than just doing this directly. Get size just gets the size. Then we have get pixel, which isn't used either. We have render noise. This is literally the most important function we have, and it takes in noise, if the color should be on or not, the smoothness, and iterations. Here we take whatever the noise is, because noise is an interface, and here we take in whatever kind of noise we have, and we also have an average, which averages out the values. What it does is let's say you have, imagine, let me take a pen over here. Okay, you have 4 indexes, 1, 2, 3, 4, and this middle one will be the average of the 4 surrounding it, which is pretty simple. There are other ways of doing this, but this is the simplest way I could think of, and it's quite efficient. Okay, let's go back, and we have a vector of noises, so we can go through iterations. So if the iteration is below 0, then we set it to 1, because if it's below 0, then it's really bad. The code will flip out. Then we go through the iterations, push back 4 different noises, like generate 4 of them of the same kind. Then we just average them out like we did with this, but we do it with different noises. Now smoothness just does the average however many times the smooth value is. Then we set the colors. So how noises, I haven't explained how noises works, but how it specifically works is that you have a vector of values from 0 to 255. This can be set randomly or otherwise. I will explain this more in depth when I talk about the noises functions. Otherwise, if there's no color, just display them in black and white from 0 to 255. 0 being black and 255 being completely white. Okay, let's move on to our first inheritance of the noise function, the basic noise, which is extremely basic. It gets a vector array, it makes one, it gets the side of the screen, and it's extremely simple. Okay, so you get a random value with the seed of I, and that's about it. Each time the I increases, so that's why if we run it, let me run it and run in the background. Okay, srand is not random at all, so it will create these patterns, because once I reaches a certain point, it will go back to the beginning of the randomness. Okay. Yeah, let's move on to the second one, which is random noise. Random noise gets some truly random noise. Okay, we get any value for any random value from 0 to the 55, and we set it to the pixel. As you can see, it doesn't make any sense, but you can make it somewhat sense if you smooth it out. Let's go like twice, thrice. Kind of looks like something. So at least it does some more work. Okay, next up we have linear wave noise. How linear wave noise works is, let me draw it out for you. Okay, so imagine we have a graph. And what we want is to have some noise, like a wave. So instead of like the random values that can be like one value here, one value here, one value here, all at random, this one is linear, like noise, actual waves. So how do we do this? We have our wave starts at 128. It starts, let's say this is the starting point. And each time we get a random value. But instead of setting it, we look at it. Hey, is it below 0? Is it below 50? Or is it above 100? In this case, we have value from 0 to 100. They're all random. If it's below 50, we take the step and we increase it by 10. Else, if it's under 50, we decrease it by 10. Now, after that, to increase the thing, so let's say we're right here, and our value was increased by 10. So next step will go up by 10. If it's again above 100, we go up by 20. So we go up like this. And if it's again up, we go up even higher. If it's then below, we go again like this. If it's below, we go again like this. And then it starts to go down. You go down, and then you go up, and you go down, and you go up. It looks a lot smoother than this, but yeah. There is also the thing that we count for. If we get 4 values in a row that are above 50 or below 50, we just set it back to 0. That fixes it going way farther than it needs to be. Okay, so as you can see, it turns out to something like this. Let's reset the smoothness. Now, this does not look like waves because our array goes through iterations like this, through the side, goes right and then begins all to the left and then goes all to the left. And each line of pixels is a line, but not the whole. So we need to find out a way to deal with that. And then we get to debug noise, which is a fix for that. Okay, we have 2 functions, left diagonal and right diagonal. Left diagonal is the simpler one, and as the first one I implemented, it's how it works is it does the same thing, but the values, the wave is only set to random for the first line up here. Then what do is we find a random value for the pixel behind it. Okay, so let's say here is the line above the first line. Okay, so let's say we're this pixel. You look at the value behind you and you look at the value above you. Now you will be the average of these two. This way we will have waves that are smooth and will go in this direction. But the thing is, they will look like waves smooth, nice, but they will all go like this in this direction. So how do we fix this? Well, we go back and we make a right diagonal, which would go like this. But if we do that, the values will average out and will look flat. So we'll get the same thing, but not, instead of going like this, they will go like this. So how do we fight against that? Well, we get the right diagonal will not be exactly diagonal. It would be slightly tilted. So instead of getting the value right here and this one down here and average it out, we could get this value right here and this one right here, or this one right here and average it out with this one right here. This will make the tilt a lot better. But how do we get it to go in this direction, you may ask? Well, we take this, we tilt it, and then we switch it around this direction. So we flip it 90 degrees. Now, how do you combine them? Well, we average them out. We average this wave with this one 2 times, and we get something like this. Now, you can still see the pattern somewhat, but if you put the color on, it looks pretty damn good. Okay, if we go to 3 iterations, it looks like pretty decent terrain. Maybe there's a lot of water, but that is not the fault of the noise. It is the fault of the coloring, which you can set as you wish and is not related to the noise. Okay. I just noticed that I haven't explained to you how not true random works. Okay. Random gets a it's just basically a random generator. It's MT19937 RNG random device. It's pretty basic. It just gives you a number every time, and it has 2 ways of doing it, from 0 to 100 or from start to end. Whichever 2 values you want, it will give you a value between those. Think about it, this is kind of useless, but could be useful. Not. Okay. Now, that's basically everything about the code. You can look again at here. This is how I implemented this explanation right here, if you want to take a look. And yeah, that's about it. Thank you for watching.